Imagine looking up from Earth and seeing the stars bend. Not flicker, bend. The constellations would stretch into arcs. Galaxies behind the darkness could wrap around a glowing ring. And across the sky, a black circular shadow would grow, not like a planet approaching, but like a hole opening in the geometry of space. Then Earth would begin to change. The oceans would rise, the atmosphere would bulge, and the ground would flex under an unequal pull. At the center of this impossible view would be a black hole, an object so compact that beyond a boundary called the event horizon, even light has no path back out. So what if Earth fell into one? Would the planet be destroyed immediately? Would time stop? Would distant observers watch us freeze forever? The answer depends on one detail more than any other: the black hole's mass. First, forget the idea that a black hole is a cosmic vacuum cleaner. At a distance, its gravity behaves like that of any other object with the same mass. If the sun were replaced by a black hole with exactly the sun's mass, Earth would continue along almost the same orbit. The sunlight would disappear, but the orbit would not suddenly collapse. The danger begins when gravity differs dramatically across the planet. That difference is called a tidal force. The moon creates ordinary tides because it pulls more strongly on the side of Earth facing it than on the far side. Near a black hole, the same effect becomes extreme. For this thought experiment, imagine Earth has been knocked from its orbit and is falling inward. We will compare two destinations: a stellar mass black hole, roughly 10 times the mass of the Sun, and a supermassive black hole containing millions of suns. The planet is the same, but the final journey is radically different.
A black hole would not appear as a solid black sphere hanging in space. Most of what we would see is what its gravity does to light. Stars near it would look displaced. Light from behind it could bend around the sides and form arcs, or, with perfect alignment, a bright Einstein ring. If hot gas surrounded the black hole, an accretion disk could glow around the shadow. But a black hole can also be quiet and nearly invisible if there is little matter nearby. As Earth falls closer, its path would depend on speed and direction. It might spiral inward, swing around the black hole, or take a curved path before crossing the critical boundary. Earth would still carry sideways momentum. The black hole would not pull it straight like a stone falling from a roof. It would reshape the meaning of a straight path. The first planetary warning would come from the oceans. The near side of Earth would feel a stronger pull than the far side. Seas would migrate across continents. The crust would flex. Earthquakes would spread as the solid planet responded to a changing gravitational field. The moon would lose its familiar relationship with Earth. Satellites, with their fragile orbits, would be disturbed first. Some would fall inward. Others would be thrown away. The moon could follow a new orbit, escape Earth entirely, or become part of the black hole's larger gravitational system. The atmosphere would stretch toward the black hole, heat up, and begin to leak into space. High above the clouds, particles would stream away in a growing tail. Earth would not need to break apart all at once. It would only need to be pulled harder on one side than the other until it stopped behaving like a stable world. Now consider a black hole about 10 times more massive than the Sun. Its event horizon would be only a few dozen kilometers across. The black hole would be small in size, but extremely compact. Near it, the tidal gradient could become lethal before Earth reached the horizon. Matter would be stretched lengthwise and compressed from the sides. This is often called spaghettification. For Earth, the atmosphere would go first. then the oceans, then the crust and mantle. Mountains would become long ridges. Global waves would race across a planet that was no longer able to hold its own shape. The near side would accelerate ahead of the far side, twisting the planet into a stream of rock, molten material, gas, and fragments. There would be no single planet left to rescue, only a ribbon of matter falling inward. And eventually, that ribbon would cross the event horizon. This is where the story becomes strange. A distant observer and Earth itself would describe the fall differently. From far away, Earth would appear to slow as it approached the event horizon. The light reflected from the planet would become redder. Each image would arrive weaker and later than the previous one. Earth would seem to fade into darkness. But Earth would not experience an infinite wait at the horizon. In its own local frame, the planet would continue across the boundary after a finite amount of time. The horizon is not a physical wall. There is no surface to crash into. It is a boundary in space-time, beyond which every future path leads deeper inward. Light could bend into multiple images of the outside universe. For a final moment, the sky would look like the universe had enfolded around a hole.
Now, replace the stellar mass black hole with one millions of times more massive than the Sun. Its event horizon would be enormous. Because the tidal gradient changes across distance, the difference in gravity between Earth's near side and far side could be weaker at the horizon itself. That creates one of the most counterintuitive results in black hole physics. Earth might cross the horizon of a supermassive black hole without being instantly shredded at that exact boundary. The sky would still be distorted. The black hole shadow would dominate the view. Communication with the outside universe would become one-sided. But the strongest tidal destruction could happen later, deeper inside. A small black hole can tear Earth apart before the horizon. A supermassive black hole may make the crossing feel calm for a short time, but only because the fatal gradient lies farther inward. Earth would not be the only world in danger. The moon's orbit would become unstable. Satellites would be stripped away. The planets would follow different paths depending on their speed, distance, and angle of approach. Some could fall inward. Others could be flung outward. A planet that avoided the horizon might still lose its orbit or atmosphere. If an accretion disk surrounded the black hole, Earth's debris could enter the hot gas. Friction would convert orbital energy into heat. Rock would melt. Water and other volatile compounds would evaporate. The debris could become a bright stream circling the black hole. But an accretion disk is not guaranteed. If the black hole were isolated, Earth might disappear with very little light at all. Sometimes, the most terrifying ending is quiet.
Crossing the horizon would not be the same as reaching the center. In the simplest classical model, the singularity lies deeper inside, where space-time curvature becomes extreme. But this is also where scientific certainty must become careful. General relativity describes large-scale gravity, while quantum physics describes the microscopic world. At the singularity, we do not yet know how to combine them. So the honest answer is not that we know exactly what Earth becomes inside a black hole. We know that it cannot return once it crosses the horizon. We know its matter and energy contribute to the black hole's mass, spin, and charge. We know its signals cannot escape back to distant observers. But the final interior description remains an open problem. That uncertainty is a boundary in our current understanding of nature. So what if Earth fell into a black hole? Near a stellar mass black hole, Earth would likely be torn apart before crossing the horizon, stretched into atmosphere, ocean, rock, and molten debris. Near a supermassive black hole, the planet might cross the horizon intact enough to notice the crossing before tidal forces destroyed it deeper inside. To the outside universe, Earth would redden, slow, and fade. To Earth, time would continue until the planet could no longer remain a planet. And beyond that point, our equations become incomplete. Black holes are not monsters waiting to swallow everything. They are physical objects governed by mass, momentum, and geometry, detected through nearby motion, glowing matter, gravitational waves, and bent light. The danger begins because black holes reveal what gravity becomes when matter is compressed to an extreme. This is Mind Astray. Stay curious. The universe becomes most mysterious, where familiar ideas stop working.